Okay, I'm gonna go back and keep going. Got a little bit more to cover today. So far, digital systems, not so bad. I speak for all of you because I too was a student at one point in my life. And I know how this is. This part is where things go like, electronics aren't that bad. I can put numbers together and make 2. I've been doing that since I was 3. So this part isn't so bad. And now we're going to take it and we're going to push this concept a little bit more. And it's still not going to be so bad. In fact, like I said, this is the easiest part of our course. We talked about resistance, and resistance is harder than digital systems in my opinion. Because resistance is like you have to do actual math and you have to come up with equivalent digital and then it's blah. Here we do have to learn a very interesting form of math called Boolean Algebra. But even then it's interesting. So let's go ahead and talk about how do we use the information we just learned. Okay, well, first of all, we learned you can represent numbers as binary numbers. Right? Okay, that's fun. We also learned that you can actually represent characters as strings of numbers. That's what ASCII is. It's a representation. And if you were to put them all together, you could create entire words with digital numbers. Now, I don't really want to go look up ASCII code, but you could look up the 8-bit ASCII digits that represent every single one of your keyboard keys, if you really wanted to. And we could sit down here and we could write entire words. But now that we understand this, this is information that is storable. Okay, the idea behind binary numbers is that we can store whether or not a voltage has been placed on something like a capacitor, right? I mean, all you need to do is just go lick that thing. You know whether or not there's charge on that capacitor. Disclaimer, do not do that. Just have to say that because I'm posting this on YouTube. But you can figure out whether or not charge is being stored. And as long as you have a threshold pain limit of, man, that was painful enough, there had to be a charge there, you could figure out whether or not it's being stored. Okay? And this is the beauty of computing systems. Computing systems have found ways where they can store an electric charge on a nanoscale microstructure, which basically means you either do or do not put an extra electron into a lattice of material at a certain location. And when you get down to it, I mean, you can put a lot of extra electrons or on something. And that's how memory is stored. We've been able to come up with memory systems off of this. We can't do that for an analog system. We haven't figured out how to do that for an analog system. How do you store the number 32 in an analog system? How do you do it reliably so that when it comes out over a period of 2 days, it doesn't come out reading as 29 instead of 32? We don't know how to do that. But we do know how to read whether or not it's a voltage or not a voltage. That one we got. Okay? So this becomes storable. And because there are many benefits to it being storable, we can then take it and we can make it calculable, which means that we can do math with it. If you can store it, you can then retrieve it and do something with it. So how do we add this? How do we add this and this? Does this just equal 1, 0, 2, 2? No. This ends up equaling 1, 1, 1, 0. Well, that's gross. How do we do calculations with this? Well, we're not doing foundational algebra anymore. This is hexadecimal addition. That's what this represents. In a binary system, we have a different method of doing math. Okay? And this different method is referred to as Boolean Algebra. There are 4 basic Boolean math expressions. I include the 4th one just because it's fun. Your first one is called AND, which is represented by a plus symbol. Your second one is OR, which is represented as a multiplication. So I'm going to go ahead and put an asterisk there because it's a multiplication. Your third one is a NOT, which is represented by a bar that goes on top of a letter. And your last one is an exclusive OR, which is represented by a circle with an X in it. Okay. And that 4th one, it doesn't really show up in math equations very often. Just FYI. Most of our math equations, in fact, all of the math we're going to talk about in this class, only uses these 3. This one just exists because you can't really get this nicely from these 3, and I think you should know about it. So that's Boolean algebra. Nice. Okay. So now what? Well, I'm going to show you what each one of these actually looks like and what they do. In Boolean math, we have to be able to add digits together. The problem with a binary number is if it's a 1 and you add it to another 1, you should be able to get 2, which means that that digit then becomes 0. So if you do get 2 1s, you get 0. But if it's a 1 and a 0, you get a 1. And that's one of the reasons why we use Boolean algebra instead of hexadecimal algebra systems. Okay? So let's go ahead and say I have 2 numbers, A and B. I'm going to bring them into this switch. This right here is an AND switch. Shockingly. In this AND switch, I'm going to add them together. No, dang it. Oh. This is a multiplication. This is an add. My apologies. AND is multiplication, OR is adding. I told you that exactly backwards. Not that it's going to change anything on your end yet. But I'm going to take these 2 and I'm going to multiply them by each other. And I'm going to take A times B is equal to C. Now, know that A and B can only equal 1 or 0. So we have 4 different options that we can have here. If A is equal to 0 and B is equal to 0, then C is going to be equal to, what's 0 times 0? 0. If A is equal to 0 and B is equal to 1, what is 0 times 1? It's equal to 0. If A is equal to 1 and B is equal to 0, what is C equal to? It's 0. Is that what you said, Gabby? Yeah, that's what I thought. If A is equal to 1 and B is equal to 1, what is C equal to? 1. So we have 4 different values that we could write out of this. 4 different combinations of A's and B's. They can either be 0 or 1, and these are all 4 of the combinations. Of these, there is only one option by which C can equal 1. And that one is only if both A and B are equal to 1. Hence the name AND. A and B, then C. Okay? There is a simpler way of writing this, and it's called a truth table. This marker sucks. You suck. I'm done with you. Oh. If I got points for hitting the rim, I'd have so many points. So the simpler way of writing it is A, B, C. We draw a line here to represent that these are the things we put in, and these are the things we put out. So this is inputs and outputs. Inputs, outputs. And here, because we only have 2 inputs, that means we have a total of 2 to the second options that we can get out of here. 0, 0, 0, 1, 1, 0, 1, 1. You'll notice that in this truth table, I have written this in binary form, counting from 0 to 3. Shocking. It's just generally how truth tables do it. Okay, and here we know it's 0, and then it's only 1 if A and B are 1. So that is the truth table for an AND switch. If you think about it in Boolean logic, true and false statements, if A is false and B is false, then C is obviously going to be false when you apply it to an AND. If one of these is false, it's going to be false when you apply it to an AND. Both of them have to be true for an AND to produce a true statement. So we do Boolean algebra a lot in coding. All right, let's do the next one. A, B, and here, instead of going into an AND switch, I'm going to draw this awesome little Star Trek figure, which this rounded half circle is an AND gate. This Star Trek figure triangle thing is an OR gate. And then we'll have it output to C. And here, the Boolean algebra expression is A plus B is equal to C. So let's go ahead and draw a truth table here. We'll have our inputs and our outputs again. A, B, C. We have our 4 different values that it can possibly be. 0, 0, 0, 1, 1, 0, 1, 1. And then we have our C output. So, what is 0 plus 0? It's 0. What is 0 plus 1? It's 1. What is 1 plus 0? It's 1. What is 1 plus 1? It's 2. In a binary system, we represent that as a 1. So the truth table for an OR switch is if either A or B is on, then the output is also on. What this means is if we took a measurement at some instance in time, and we measured A, B, and C simultaneously, A would be at 0 volts, B would be at 0 volts, and C would also be at 0 volts. That's what we would expect out of this system. Okay? Similarly, if we took an instance at time, we would measure A, B, and C all at once. We would see that A is equal to 0, B is equal to 1, or A is equal to 1, B is equal to 0. We would expect to see C equals 0 at that exact same time. Okay? That is an OR gate. Now the third one is not. Here, we only have one input. And instead of having the kind of curvy thing here, we just have a triangle. And we put this thing on it, this circle on the end of it, to make it look like a sideways Christmas tree. And this is called a NOT gate. And here, you only have one input and one output. So the truth table, oh, and here, the Boolean algebra statement is we put a line over the top of A, and A naught is equal to B. That's the way that we write it in Boolean algebra. Okay, the truth table here, because we only have one input, we're only going to have 2 entries in our truth table. So we got our inputs and our outputs, and our inputs go from 0 to 1. What would you expect the output of A naught to be when A is equal to 0? Why do you say 1? It's not 0. Yeah. This is 1. So what we would expect for A naught when A is equal to 1? It's not 1. It's 0. Okay? Those are 3 of our fundamental tables. Last one gets a little weird. Last one, we have, oh, an exclusive OR. Dang it. Gotta remember what the, that's right. So what we're going to do is we're going to build that fun Star Trek thing again, but we're going to give it a force field on the backside. Okay? And what this statement is this is an XOR, which is an exclusive OR gate. The representation of this is A circle cross B is equal to C. Or I guess it's a circle plus, not a circle cross. We don't use this very often. My apologies. Well, that's two mistakes in one lecture. Sadness. Now the idea here is, this is an OR gate, which is why it's drawn like an OR gate, except there is a difference. It is exclusive in the fact that if A or B, but only A or B, then C. Okay? And so the truth table, again, you have your 2 inputs, your 1 output. You're going to have 4 entries, 0, 0, 0, 1, 1, 0, 1, 1. Your truth table looks like this, 0, 1, 1, 0, where C is only on if, and only if, one of your inputs is equal to 1. If both of them are equal to 1, then C is 0 again. So this checks whether or not A and B are the same thing. If they are the same, then it is no longer a valid output. Okay, that is the exclusive OR gate. We doing good? Okay. So, everything we do in Boolean algebra can boil down to these systems, where we take and, or, and not, and sometimes XOR, and we plug all of them together, and we come up with algebra statements. Okay? And this produces very interesting things. Now, I want to go into the actual digital circuits before I get into the Boolean algebra, because to me it makes a little bit more sense to approach it from a circuits standpoint. Here, I could touch a multimeter to A, and I could touch a multimeter to B at the same time. And I could read what their outputs are simultaneously. And from that, I can figure out what both A and B are. I could actually measure the output of this truth table. And that's kind of the way that I want to approach this. Boolean algebra it's a way of representing how this digital system actually works. Okay, so let's get a little funky. So we have 4 inputs this time. A, B, C, and D. We put all of them into one AND gate, and we produce an output E. Little funky. Now there are AND gates that have 4 outputs. There are AND gates that only have 3 outputs. There are AND gates that have 2 outputs. I believe there are actually AND gates that have 8 inputs too, but that's getting a little crazy. But we have this system, and we want to write a truth table for it, because we want to know how is this system going to behave based on how A, B, C, and D change. Okay, first thing we're going to do is we're going to write all of our inputs and our output. Inputs here are everything on this side that change. Outputs here are the derivations of your inputs. There are some calculations that go on in here that produce your outputs. Okay, how many different entries to this are we going to have in this truth table? Anybody want to venture a guess? Why did you just say 16? It's 2 to the 4th. Yes. You got the right number, but yeah, it's not times. It's 2 to the 4th. And he's right. We're going to go and represent the numbers from 0 to 15. Oh boy, I'm halfway there. Got it. Only took me the entire board. Nice. 16 entries. Okay, once again, I'm a patterns guy. I love patterns. This thing repeats where if you look at only this column right here, it goes 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, the whole time. If you look at this column, it's 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. This column, 4 zeros, 4 ones, 4 zeros, 4 ones. This column, 8 zeros, 8 ones. If we were going to continue building on this, and have 5 inputs, 6 inputs, 7 inputs, 8 inputs, you'd expect your next column to have 16 zeros and then 16 ones. And then your next column, 32 zeros and then 32 ones. And no, I am not writing those on the board. No, you will not be doing those in class. That is insane. But that's how the progression goes. It's very much a pattern, and they love patterns. Now the question is, we plug all 4 of these into an AND gate, what do we get? When would you expect this system to be on? Not you. Huh? Just this last one. Why only here? Yes. Some people get tripped on, but we have A and B here. Why doesn't that turn on? It's because this isn't an A and B or A and C or A and D or A, B and C or B and D or C and D system. This is an A and B and C and D system. Okay? Gabby is right. This is the only time it turns on. All of the rest of those are zeros. I have to write 0 15 times. And that's our truth table. If we plug in A and B and C into the system, we would expect that E would be 0 if D is 0. If any one of these incidents are 0, we would expect the opposite. Now let's get a little crazy. I'm going to take this system, and you know what? Instead of rewriting the entire everything, I'm just going to go ahead and erase on my end because I'm a lazy man. We're going to take the output of this, plug it into a NOT gate, and have that be E. Another way of representing that, by the way, is A, B, C, D going into an AND gate that has a circle on the end of it. Okay? This is referred to as a NAND gate. N-A-N-D. NAND. But it's the same thing as this. If we did this system, where would we expect it to be on? What do you think, Jonathan? 1, 1, 1, 1, 1. The only place it's off is this last one. Every other place it's on. It is the exact opposite of the truth table that we had for the AND gate, which is why it's an AND gate. It's like it's like if AND had a nemesis. This would be NAND. Okay? Does this make sense? We can actually take these, plug them into other digital gates, and make more complex circuits. And we're going to do that. Dylan says no. Dylan says no, so I guess we're done. I'm going to teach you about memes now. Now we're going to go ahead and take a 10-minute break. To which of you want to sit and listen to me talk about memes.